Okay, so once again, I want to say good evening to everybody. I'm Joe Deli Carpini, the Science and Operations Officer, and we're going to talk all about tornadoes tonight. And just to give you an idea where this comes from, this is part of a study that we are doing between the National Weather Service in Albany and New York City, as well as University of Albany, which was formerly SUNY Albany. And this is kind of our part of the um, study that focuses on tornadoes in southern New England. So the challenge for us is, and you probably know, that tornadoes in New England are much different than those in the plains. They form in different environments. They tend to be weaker and short-lived, just kind of on the order of minutes most of the time. They also usually spin up from the ground, not always from above, like the big ones out in the plains. And the strong and really longer-lived tornadoes are fairly rare around here. You have to go back to the Springfield tornado in 2011, and before that, Worcester in 1953. So these are very, very rare events. But historically, we kind of discovered that tornadoes were poorly forecast in our area, and a real challenge was issuing tornado warnings with any lead time. A lot of the times, forecasters were reactive to kind of what they were seeing on the radar. They would see the couplet form, and then it was too late. The tornado would be on the ground. So we wanted to go through this study to kind of look at the environment, look at some radar data, and kind of get a little more proactive where we could issue warnings with lead time. So I just want to review tornado formation, and this is kind of how it begins. So, we have what are called horizontal rolls, which occur when you have strong winds aloft and weaker winds near the ground. You get kind of this tube, which is aligned horizontally, and eventually it gets kind of ingested into the storm, into the updraft, and it takes on a more vertical appearance. And then finally, if it gets strong enough, you can have the tornado form. But something that we found out is that recent research has shown that it's actually the cooler air from what's called the forward flank downdraft that can be an important source of spin for the tornado as it intersects with this air coming into the storm. So again, a lot of times we thought it was this what's called rear flank downdraft on the backside of the storm that would curl around and form the tornado. And in many cases it does for the larger plain storms. But for the smaller ones around here, it's actually the colder air coming out of what's called the forward flank downdraft, where you have the rain and the hail in the storm that meets up with the air coming in, and that is where we get our spin. So that's kind of something that's going to have a little more research done in the next few years, but certainly something that's different than kind of what we learned back in school. So let's talk about the study. This updates some previous work that we had by some students done back in 2008 and 2017, looked at favorable environments for tornadoes in southern New England to really help us, again, improve the warning detection and the lead time. It includes 39 tornadoes. We actually added 27 of them from 2018 to 2021. It's active few years. There were 21 of which were EF zeros, and we ended up removing one that was a cold air funnel. It just wasn't the typical thunderstorm type tornado, and 2 landfalling waterspouts that were almost not even detected by the radar. There were 16 EF1s, and you're probably familiar with the higher end ones. One was an EF2 in Revere in 2014, and another was the EF3, which was the Springfield to Brimfield to Munson tornado back on June 1st, 2011. So the later study done in 2017 actually looked at radar data as well to kind of develop a warning decision guide for our forecasters to use. And we analyzed the recent events to see if any adjustments were needed to that. So to show some of the background, and you can find this also on YouTube on our tornado, kind of our Southern New England Tornadoes webinar, which we did a couple of years ago. But just to kind of reiterate, the initial study back in 2008 separated all the events by the synoptic or larger scale classification. So type A here was a closed low somewhere over southern Ontario or near the Great Lakes. Type B was kind of a weak open trough near the Great Lakes. Type C was more of a deep trough in the eastern U.S. that extended all the way down to the Gulf Coast. And D was our tropical remnant systems. And until last year, we didn't have very many of those at all. And then type E was the cold pool, which we're really not going to talk about in this study because there was only one. So then we went and looked at some of the environmental parameters from the Storm Prediction Center mesoanalysis page and some observed soundings. The main really factors were instability, shear, and moisture. Some of the other parameters were less conclusive that we looked at before, such as temperature, dew point, and even the jet stream strength. So we created tables for each of the synoptic classes, A through D, and then summarized them for all the tornadoes combined, and then separated out for EF0 and EF1 and higher. So when we look at that, we'll show some graphics next. You can see most of the EF0 tornadoes here, as shown in the blue bars, were associated with either the closed low, the open Great Lakes trough, or the tropical remnant for the most part. But the majority of the higher end tornadoes, so EF1 and higher, were associated with closed lows. So that's really the pattern you want to look for when we're talking about the higher end tornadoes. You can see some with the open Great Lakes trough and some of the deep eastern trough, but by far the majority was with the closed lows. So looking at it another way, kind of with a pie chart, you can see there's nearly an even split here for the EF0 tornadoes. So again, with the closed low, the open Great Lakes trough, and even the tropical remnant. So those were just about the same for the weaker EF0. And then when we go to the EF1 and higher, you can see a clear majority here for the closed low, about 61%. Followed by the eastern trough and the open Great Lakes trough. But there was only one tropical remnant case. That was actually Tropical Storm Allison back in 2001, but we didn't have any of the analysis data for that to kind of include it in the study. So if we put it all together, here are the environmental parameters for all of the events. And really the key points here are relatively low CAPE, which is our instability, high shear, and high moisture. So you can see for all the classes here, these are kind of the average numbers. The CAPE values are typically right around 1,000, which isn't tremendously high. The 0 to 3 kilometer CAPE, so we're looking in the lowest levels. Typically the rule of thumb is 50 or higher, but this is showing about 74 or higher. So anything above that is pretty significant. And then when we look at the kind of the spin in the atmosphere, it's the storm relative helicity. So the 0 to 3 kilometer layer, you can see it's well over 150. 0 to 1 kilometer, it's over 100 for the most part. But some of those vary depending on the case. And then the precipitable water I'll focus on too, about 1.5 inches. And you can see that's pretty much straight across the board. And the other important one is this LCL, which is the lifting condensation level. So that's the height which you would lift the air for it to condense into a cloud. And that's important because the lower the LCL, the easier it is for the tornado to touch down. So this is in meters. So typically our rule of thumb was 1,000 meters or less, but really from looking at the study, you want to be almost 750 meters or less to really be favorable for tornadoes here in southern New England. So then if we split them out, we'll look at just the EF0. You can see the CAPE values are a little bit higher, but the shear is lower. So you've got a little more instability, a little less shear in this case. You can see these values are definitely a little bit lower, not by much, but they are. And the LCL layer is maybe a little bit higher, if anything, but overall, again, higher instability and then less shear. And then I think this will also make sense if we look at the stronger tornadoes. It's lower instability and a lot higher shear. So there's a lot more spin in the atmosphere for these higher end tornadoes, and I think that kind of makes sense. So in summary here, just to show the difference, the EF0s, there's a fairly even split with the large scale pattern, the closed low, the open trough, and tropical remnant, whereas for EF1 and higher, the closed low is most dominant. As far as instability and shear, again, CAPE is the instability. We'll call it moderate for the EF0 tornadoes, about 1,000 joules per kilogram, which is the measurement that we use. And the shear is well over 100. And the lifting condensation level, that LCL, is about 750 meters or lower. Whereas for the higher end tornadoes, you have lower instability, but you have a lot higher shear. Notice how these numbers are quite a bit higher than what we see on the left. The LCL is a little bit lower, but not by much. And again, it's rare to see these higher end tornadoes in tropical remnants. We haven't seen really one yet, or even cold pool environments, but a landfalling hurricane certainly could bring one of that with us. And it's also important to note, and this was in the original study, that the values of CAPE and shear, they can vary widely, and they often trade with one another. So a day with low CAPE or low instability needs higher shear, and a day with higher CAPE, you can get away with lower shear. And it's that 0 to 3 kilometer layer, kind of the lowest 7,000 feet, which really seems to be most important for our tornadoes. And that makes sense because they spin from the ground up, not from the top down. So those are the layer, that's the layer you really want to focus on for the CAPE and the shear. All right, so let's move on to the radar analysis at this point. So what we did was we took a whole database of all the tornadoes, all 39, and we used the Taunton radar, the K-box radar, and had the best sampling for all of these tornadoes compared with Albany or New York City. 4 of them were associated with squall lines. If you remember, October of 2021, we had that squall line move through with several tornadoes. Others were what we call mini supercells or clusters of storms. The exception being June 1st, 2011, which were kind of the typical plains supercells. And then again, we removed a few of the weak EF zeros, the cold pool, the water spouts, because they just weren't representative of other, conditions. And some of the velocity data too was poorly sampled. Again, if you remember from our radar studies, if you're perpendicular to the radar, you're not going to see much in the way of velocity. So in those cases, we couldn't include those as well. But we came up with a whole spreadsheet of all the events, 39 tornadoes. And just before we get into it, I'll just go over some quick definitions that we use. The SRM couplet is a storm relative motion couplet. It's also known as rotational velocity, and that's just the rotation relative to the storm. So we take the max inbound number, or the brightest green, the max outbound, the brightest red, and divide it by 2. So an example, if we had here, for example, 40 knots of inbound north of Yarmouthport, 30 knots to the south, we'll take the sum and divide it by 2, which is 35 knots of rotational velocity. And then the NROD is the normalized rotation, which kind of takes into account the depth of the circulation within the storm. So the higher the value, the stronger and deeper the rotation is, the more favorable it is for tornadoes. Something else we'll talk about is the TDS, the tornado debris signature, and that is the radar confirmation of a tornado. You have to have the following in order to meet that. So you have to have high reflectivity, at least 40 dBz, which is typically the yellow or reds. You have to have an SRM couplet, which we see on the upper right, the greens right against the reds. On the lower right, you have to have lowered CC, so the correlation coefficient. Typically anything lower than about a 0.85 for the greens, the blues you're looking for. And if you want to add confidence, lower left is differential reflectivity, or ZDR, and notice you've got some gray, which is near 0. That just adds confidence, but it's not required. The actual requirement are the reflectivity, the couplet, and the lowered CC all in the same place. So that's important to remember. All right, so let's go through some of the radar data here. We're going to look at couplets and NRODs. So when we're looking at all the tornadoes, the typical couplet was about 31 knots of rotational velocity. The EF0 is a little bit lower, which we'd expect, around 25 knots. And the higher end tornadoes were much higher, around 37 knots. And you can see the NROD kind of follows a similar trend, about 0.8 for all tornadoes, lower for the EF0s at 0.6 and 0.9 for the higher end tornadoes. So overall, our earlier conclusions from our studies showing a rotational velocity 25 to 30 knots, the NROD 0.6 to 0.8 still seems to be good, even when you're closer or farther from the radar. So we'll show that a little bit in the next slide. So again, as a reminder, as you get farther from the radar, notice the cone gets bigger that it's sampling, so you don't sample as well as you do closer to the radar. But note here, the values within about 40 nautical miles of the radar are fairly similar to those of the average. So the couplet is about 32 knots, 25 knots, and 38 knots for all 3 categories, and a similar trend on the NROD. So really, if the storm is within 40 miles of the radar, you're going to use roughly a 25 to 30 knot or so threshold. And then we go beyond. Notice there's really not much difference either, so that's interesting. 32 knots for all tornadoes, 26 for the EF0s, 37s for the higher end. So, not much of a difference. If I go back here, you can see it's about the same, and same for the NROD as well. So that's good. That means we don't have to separate them out at a certain range. We can use one value pretty much across the board. Now, I also looked at it by the type. So let's look at the closed low here and see if there's any differences. Notice for these closed lows, the values are slightly higher than the average for all of the events. Notice our numbers are just a tick higher, 34 knots, 27, and 41 respectively. Whereas, for all the events, it's about 31, 25, and 37. So we're a little bit higher, but not by much. For the type B, notice the values are a little bit lower than the average, especially for the higher end. We're pretty much right around 26, 27 knots when we have an open trough moving across the Great Lakes, which is significantly lower than what you see here on the right. And in type C, our deep trough down to the Gulf Coast, those tend to be higher as well, similar to the closed low, with couplets well into the 30s, 37 knots, 39 knots, and 36. Interesting that the rotational velocity is higher for the EF0 and Type C than it was for the EF1. And that just could be, random sampling of the events. But in any case, not too far off, a little bit higher than the average, but especially for the EF0 tornadoes. And then when we look at tropical remnant, these are the hardest ones. The values tend to be much lower than average. And again, we didn't have any EF1 plus for this class, but look, only 18 knots of rotation, and and some of them was only 15 knots, which you wouldn't really think would be anything, but again, well below the average. So the tropical remnants are really all out by they're kind of an outlier when we look at the different events. Now, when we look at the range from the radar, again, we talked about there's not much of a difference, within 40 nautical miles or out, but I looked at just where were all the tornadoes placed that we looked at, all 39 of them. And the average actually was about 40 nautical miles. That's kind of our sweet spot for detecting the couplets. Notice 42 for all of them. The EF0 is a little bit closer at 39, and the stronger one's a little bit further out at 44. And this just shows, the range. The average range, if we're within, is about 26 miles, 29 miles, 23, and beyond, quite a bit farther, 55, 52, and 57. So the tornadoes from this study were about 2 nautical miles. We had one in Norton, just north of the office, in October of 2019. And as far as 83 nautical miles out in Bristol, Connecticut back in 2010. But kind of the sweet spot for the radar is about 40 nautical miles, which is kind of what is out in all the research literature. Now, the tornado debris signatures are kind of interesting here. Notice about half of this is all the tornadoes here on the left, about half of them had a TDS, regardless of the intensity, whether it was an EF0 or EF1. But note, when we look at the range, the probability increases greatly when you're within 40 nautical miles to see a TDS versus being beyond 40 nautical miles. It almost doubles, you can see here, for all the tornadoes, and especially the EF0s and even the EF1s. It's about twice as much. So you're more likely to see a TDS within about 40 nautical miles than you are to see one beyond. You got about a 1 in 3 chance when you're beyond 40 nautical miles. So we'll look at our tornado guide, the tornado warning guide, and this actually confirmed a lot of what we had from back in 2017. Again, we use our rotational velocity couplet, add some points. We look at the NROD, add some points. And then there's a couple of environmental corrections. One is that low-level helicity. One is the precipitable water. I think in the 2 inches, we could probably even lower it about 1.5 inches. And then if the LCL is higher than 1,000 meters, or roughly 3,500 feet, then we take a point off. That's because it's dry, harder to get the funnel down. But the scores do loosely, they also loosely correlate with tornado strength, but not enough so that we could say with any confidence, if you have a really high score, it's going to be an EF2 or EF3 tornado. But the Storm Prediction Center is actually working with a tool that uses rotational velocity, uses some environmental factors to come up with a prediction of intensity. So they're going to take a lot of our data to kind of help calibrate that for tornadoes here in the Northeast. Obviously, it's going to be calibrated for the Midwest, but we're going to give them all of this data here that we've collected to kind of help them calibrate that. So in the next couple of years, we might actually be using that in our office to kind of loosely come up with a tornado intensity estimate to use in our warnings. So to verify the warning guide, this shows all the scores again. And what you have is in the blue is all tornadoes, the yellows are EF0s, and the whites are EF1 higher. And the scale is on the left. But you can see for all tornadoes, the typical score is about a 12, and that fits in with our greater than 50% tornado probability. For our EF0s, it's about an 8, which fits into our TOR possible. So remember, for the EF0, we typically do a severe thunderstorm warning and mention a tornado possible. And then for the EF1 and higher, it's usually off the charts. Tornado likely, it's beyond the scale of 12. So you can see the break, not much of a difference within 40 or beyond 40 either. So, to us, this says that the scorecard works pretty well, and we can keep using it to help with detection and lead time especially. And then we also broke it down by the type, just so you can see that. Again, all tornadoes on the left, the EF0s in the middle, and the EF1 plus are on the right. Not much of a difference, but you can see, again, fits in pretty well. The open trough, the numbers are a little bit higher, as are the deep trough, but overall, works pretty well with the current thresholds that we have on there. So to summarize the radar findings, the tornadoes were detected by the Taunton radar an average of about 42 nautical miles. The average was about 39 miles for EF0, 44 miles for EF1 and higher. The average couplet was about 31 knots with a normalized rotation of 0.8. And you can see the differences there between the EF0 and EF1. There is a bit of a difference, especially with the couplet. The type A's were much higher couplets. The type D's were much lower, so knowing the environment is certainly important. And the tornado debris signature was observed for about 50% of all tornadoes at an average range at about 42 nautical miles. And notice that the detection increases to about 60 to 70% if you're at about 20 to 30 miles from the radar, and lowers to about 30 to 40% once you get outside about 50 to 60 miles. But overall, the thresholds in our tornado warning guide are still valid. Again, the scores are kind of loosely correlated with tornado strength. So the higher the number, the more likely you have a stronger tornado. But in the study, some of the EF0s actually scored pretty high. So we can't say, with any amount of confidence that's always going to be the case. So with that, that's a look at our study. If I don't see any questions in the box, but I'll pause here and see if we have any questions before we move on to our weather briefing. Hopefully everybody can still hear me and everything's working. But I'll just pause here for a second. And of course, on the top right, that's the tornado in Munson on June 1st, 2011. Any questions out there? All right, I'll give it a couple of minutes if anybody thinks of anything. Hopefully, again, someone want to confirm that you can actually hear me? Hope I wasn't talking to nobody. Okay, you can hear me. You're here. Good. It's quiet group tonight. All right. Anybody have any questions? I know we went through a lot, but we talked about the environments and we talked about the radar signatures. And again, this study was to include tornadoes since our last study that was done in 2017 by a student. So we included 2018 through 2021. Obviously, last year we had a number of tropical tornadoes. So we wanted to get those included in the study, but really just kind of confirms what was done by our student 5 years ago, which is great. Happy to see that. And the next part of our study here is to include some of the data from the New York City office, the Albany office. They're gathering the same data that I did. And we're going to kind of throw it together. And, I'm assuming things will be pretty much the same. But, we'll kind of see what they come up with here in the next few months as we go through it. So, okay, it looks like we have one question, then we'll get on to the weather briefing. Let's see. Okay, so question from Aaron. Heard that Western Mass, Connecticut is becoming more of a hotspot for tornadoes. Also, the increasing frequency of tropical tornadoes. What's contributing to the increase? It's true. Western Mass and Connecticut is our hotspot here. There's usually more thunderstorm days, first of all, less influence from the ocean. So, you typically will see storms march across from the Berkshires. And once they kind of hit Worcester County, they tend to die out. And that's because they're coming under the influence of the ocean. The southwest winds off the water, Rhode Island, eastern Massachusetts tends to stabilize things. So, simply the more thunderstorm days you have, the greater the chance. Also, the terrain out there helps as well. The Connecticut River Valley, in particular, can help channel a lot of that low-level spin. So think about it. If you've got strong winds aloft, think 10, 15,000 feet out of the southwest or the west, and then right at the ground level, the Connecticut River Valley is channeling them out of the south. That's a big change in direction with height, and that's going to help spin up more tornadoes. Plus the terrain as well. You have higher terrain, it's easier for the tornado to touch down. So that is true. It's traditionally been a hotspot for tornadoes, and that's where we tend to see the most of them. Western Massachusetts, western northern Connecticut as well. Not so much near the coast of Connecticut, but farther inland. And in the tropical tornadoes, a couple of reasons for that. One, we definitely have been a little more active in the past couple of years with either remnants moving through or systems actually affecting us. But we're also hearing more about them too. So, everyone has social media, can take video on smartphones and things like that. So we do hear more about tornadoes than we did even 10 years ago. So a lot of times what was probably considered wind damage 10 to 15 years ago can now be classified as a tornado because we know about it and we can go check it out. But good questions there. All right, let's see. From JP, next question. Are our current conditions this summer and upcoming fall likely to result in any tornadoes? Not yet. It's been pretty dry. Obviously we're in the midst of a drought here, but we are seeing some of these cold fronts come through every few days. So, like tomorrow, for example, and I'll talk about that in our weather briefing. Um, we do have more chances, certainly. Stronger jet stream can certainly help. So if we can if we can just get enough moisture, enough instability in the area, we certainly have a chance to get some tornadoes. And, if you've been following the forecast from Storm Prediction Center, you see there's almost always like a 2% chance of tornadoes whenever we have a severe weather day. And I think tomorrow's another one of those days as well. So there's always kind of a low risk, especially when we get in these really humid air masses with dew points getting into the 70s. That's, as we showed in the environmental parameters, that's pretty favorable. So I would say, yeah, let's keep an ey out as we go through the summer here and into the upcoming fall. Even we can get tornadoes as well. All right, let's see. And Fred is saying, yeah, the heat and humidity has not delivered storms this year. Never mind a tornado. Yeah, not here in the east. The west, we've had a few, but not even there. It's been pretty sparse. So, we'll have a chance tomorrow. We'll kind of see what happens. But yeah, definitely we've been in kind of a not just a drought, but even a severe weather drought. It's been very, very quiet season. From Sydney, we're Midwesterners living in Western Mass and used to big flat space with big warning systems. How much notice is realistic for New England tornadoes if we can be predictive? Right now, for most of them, it's just going to be a few minutes. I would say anywhere, with our typical short-lived tornadoes, it can be anywhere from hopefully 5 to 10 minutes. In some cases, maybe 15 if we're really on it. The longer-lived storms, so the ones like the Midwest that we had here in June of 2011, there was a long-lived storm. We can get as much as maybe 15, 30, even 45 minutes downstream from the tornado once it forms, if it's a long-lived one. But I would say for the most part, we're aiming for 10 to 15 minutes with our short-lived ones. It's typically going to be between about 5 and 15 minutes. That's been our average over the past few years. Especially once we've implemented the results of the study in the office. So, remember with your smartphone, you'll get an instant alert when there's a tornado warning. So you'll know right away. So even a couple of minutes is good. That gives you enough time to prepare. But yeah, no warning systems out here in Western Mass, especially, or even any of Southern New England. But you'll get the smartphone alert. And hopefully, again, 5 to 15 minutes is kind of what we target on these. All right, let's see. Kevin's got a question here or two. Does the lifted condensation level below 750 help tornadoes form in New England? Yes, as well as several other factors. So yeah, again, so what the lifting condensation level is, it's the height at which the air is becoming saturated. So that's the height where you're going to start to see cloud bases form. So you want it lower. If you want a tornado, you want that to be as low as it can so it has an easier time touching down. The higher it is, the more difficult. So our research showed that it's about 750 meters. So what's that? Maybe 2,500 feet or so is kind of a good, estimate. But, sometimes it can occur if it's higher, but that tends to mean the air is a little bit drier. So it's harder to get that funnel to come down. On days when it's over 1,000 meters, you might just see funnel clouds, if anything, from that. So good question. And also, does dual polarization help with confirming debris signatures? Yes. So Kevin, as I showed you, you have the reflectivity and velocity couplet, but you also have the correlation coefficient, the lowering of that, and the near zero differential reflectivity. So the last two, correlation coefficient and differential reflectivity, are dual polarization products from the radar. So good question. Let's see, from Chaz. He knows we're in a more stable area on the Cape and Islands, but in the past we used to get many more thunderstorms. Is that an effect of global warming and the fronts having less push? Well, probably to some degree the climate change comes into it, but that's actually pretty typical. As the cold fronts reach the coast, they tend to kind of lose their punch most of the time, unless there's a really good say trough aloft, again, 10, 15,000 feet to kick the front through. So the example would be, even last week when we had thunderstorms, the front just kind of fizzled over the south coast. That's pretty typical. It loses the punch of cooler air, it runs up into the warm and humid air coming up across the Cape and Islands, and the front usually just dissipates or hangs up near the south coast. So, you'll still get your thunderstorms, and, especially as we get later into the summer, the water temperatures are getting warmer now. So as we get into August and September, the ocean is less of an influence as far as causing the thunderstorms to weaken, and in some cases it actually can energize them a bit. So Chaz, on the Cape and Islands, wait for later in the summer, August, September. That tends to be a better time for thunderstorms down there. Let's see. Question from John. Is there any correlation between climate change and severity or frequency of occurrence of tornadoes? Great question. That's actually something that's being researched now. So far, there hasn't been any correlation between the frequency or severity, but they've only been looking at a few years of data. So it's going to have to go looking at, getting to 30 years plus to really get a good sense. But so far, there's really no indication or, direct correlation between a warming, atmosphere and frequency or severity. But, again, I would go back to saying if it's warmer, we have more moisture in the air, you're going to have more thunderstorms. Obviously, the chances would increase and a stronger jet stream too. The chances should increase. But again, something that's being researched by the climate folks, and we may have more answers on that in the next couple of years. So let's see. I think that's it. Kevin just had a question about the Atlantic marine layer suppressing storms. Yes, as I just mentioned, especially early in the season, the cooler water temperatures will help weaken the storms. Later in the summer, the warmer water helps get them going a little bit. So, all right.